to do something. Time to speak about new kind of protection. It's called distance protection. What's it all about? Yeah. More lights. Yeah. Okay. What kind of beast is this? Distance protection. Why distance? Distance from where? Distance to what? Okay. Let's say I have a situation. I have a city network. So I have a quite large city network. And power plant. This problem, historical, first arrives in New York, somewhere around 1905, 1907. So power plant supplying city, there is one moment in such network. Huge difference between loads daytime and at night. When train movement stops, energy consumption drops drastically. So at night time, it's profitable only to run one generator, one machine. So at daytime, I have all machine operating and I started my schematics, there will be into prime and something like 1/4 of the longitudinal reactance. At night, only one machine. So, day by half, night, full, approximately 4-6 times changes resistance. Meaning what? I call it significant change in the fault current. This means what overcurrent protection I will have here, OCD, here, overcurrent protection, all around overcurrent protection. I will need to change settings for overcurrent protection at least twice a day. And do it really all over network. When we speak on modern distribution network, fault circuit, this fault loop resistance is mostly defined by a transformer adjusting net to 110 kilovolts network, for high voltage network. In this case, it's old historic case, but problem was power plant works directly and huge change in number of active generators. Or yeah, you can hire a special guy who will listen to the phone and switch settings every moment number of active machine works, but it's unreliable. It's really, it's not only expensive, it's unreliable. So idea started to move around. How can automatic adjustment of overcurrent protection operational settings be achieved? let's look on very simple things. 1, 2, 3, 4. My plant. Okay, switch. Single line. L. It's big. Three-phase fault. Very simple. And what will be our schematics? X prime, H prime, alpha Z1 fault. Here, voltage available to some relay and current of relay. This is night regime. In daytime, nothing changes except here we will have 1 fault. It's daytime. This voltage HQ prime alpha set divided by the prime plus alpha Z1. Voltage available at relay point is directly linked to the resistance. At daytime, they will be 1/4. So if it would be possible to adjust trip current as a function of voltage available to relay, this relay will be it will be self-adjusting or adaptive. We will see relay able to adapt to the network regime. 1 second. I start with problem. We need adapter overcurrent protection. The first idea how to solve this problem. So I need an overcurrent relay with strip current, Nostrad in Latvian, should be function of relay voltage. And what kind of function? The higher relay voltage, the higher should be a trip current. It was first idea was with balance relay. Idea to use a current balance. Do I have a current balance? 1 second. Current balance. Here it is, my current balance. So what's the idea? I have this current coil. This coil, if there is a current will be forced, this coil drags down this steel ball, and all this balance tilt, here should be contact. As how trip current is adjusted? Here I have magnet, and it creates an opposite force. This one is, how to say, to operate or work force. This one is braking, works against operation. Here is my current balance. So what can be done? If I substitute magnet with this coil, like this. If there would be a coil, this coil, this second magnet, voltage coil, will act as a contact force, will push the system up, while current pushes system down. Idea. On the one side, cylinder, and current coil. Current coil tries to swing this arm counterclockwise. This circuit will produce a trip signal. But on the other side is a second coil. This coil voltage connects to interim transformer. This transformer with taps to adjust this contact force. So this one to operate, current moment, opposite, voltage moment, but it's a braking, it's contact operate. this kind of current balance with opposite force from the voltage. Force from voltage, force from current, radius for current, radius for voltage. So if FU is higher than FE, relay will trip. And this force, coil geometry, number of lines, and setting of the tap. Can be written very easy what relays trips if some kind of current factor, current divided by voltage is greater than 1. Or I can also this factor includes radius and design constants of coil. Or what it will be? Current divided by voltage is conductivity. Some kind of, okay, it can be some kind of constant. Operation in this form is not very handy because we have operation zone outside of some area. It's better to consider it in different form. U relay divided by E relay is less than constant. This form is, more preferable, meaning what we have a trip condition for current balance, absolute value of resistance, kind of trip from Latvian Nostrad resistance. Actually, current balance is nothing else than a minimal resistance relay. Minimal resistance relay. Great. Is it good or is it bad? Is it good or is it bad? We need a way to analyze. And for analyze, special tool can be incorporated. It's a complex resistance plane. The active resistance considered real, inductive, reactive positive, and reactive capacitive negative. This is our analyzing tool. If we have a trip condition, we will see on our complex plane? Circle. Inside operation area, so railway strips, if observable resistance point is inside this characteristic. So if that two rails divided by E railway is inside this area. Okay, you see, but is it good or is it bad? How? How can we tell? Good, is it good characteristic or bad characteristic? Let's see. Let's assume we have system 1 with 2 switch and system 2. This is second line, this will be 1. Yeah, very simple setup. Active, reactive. Here. Let's assume this part we sit here. First fold at the end of the line. For simplicity, let it be line, three-phase fold. What will see my relay? Relay is here. Here sits my relay. What it will see? Resistance of the second line. Substitution schematics. A system 1. ZL1. Voltage of the relay. Current of the relay. L. Fold. Here something system 2, but it's not important. Our relay will see only resistance of the second line. Here, at approximately 65 degrees, here is the point of the fault 1. Approximately 65 degrees, 110 kilo network, at a distance of the second line resistance. Okay, more faults for the god of faults. Fault 2 at the kilometer 0. What will see my relay? Answer 0. 2. Nice. So area of operation is in the first quadrant. And what about external folds? Fold 3. What will see my relay? Voltage at this point and current from the second system. My relay will see resistance of the first line, but current flows from line to bus, meaning what it will be with minus sign. Here also 65 degrees, and here is point number 3. To make it complete, this is number 4. If it's clear, it will be 0. Internal folds, external folds. We can say what operation area. This color not good. Should be something like this. Anyway, operate here in first quadrant. Do not operate here. And how it goes with current balance characteristic. No, not good. This segment of pi will cause false 3. Not good. The first idea was to combine. K means relay, Z resistance. To combine minimal resistance relay with the power direction relay from directed over current protection. Current, voltage. So this is relay of minimal resistance current balance, and this one is a relay of angle from the directed over current relay. If you combine them, you will get what kind of characteristic? The white one is from this relay. This one will give you something like this. So effective characteristic will be intersection of them. Here in orange, I hope you can see orange. It's effective characteristic of such combined relay. It's much better because it will not operate falsely on this fold. But still not sufficient. Why not sufficient? I'll explain. Active, inductive, vector of line resistance. Let's think what this fault is not ideal line-to-line fault, but fault, let's say we have somewhere here, at a distance of half, fault with transient resistance. 3. Well, what we will see? Without transient resistance, this should be here, alpha 20. Plus, additional, I need to draw active resistance of RF. If I have characteristic like this, see what happens? Miss, do not operate. Because this radius, it goes down. This idea, this downgoing branch of the circle, this segment of circle, can ruin everything if, in case of transient resistance. So the next idea, what was achievable with analog techniques, was idea of shifted circle, like this. Not circle going through the 0 point of coordinates, but kind of shifted. Here, here stands this one, teaching relay, is for students to torture. Operates in such way, it creates an elliptic, not ideal circuit. I can make it elliptic with this angle choosable up to 80 degrees and with ellipticity on 80%. This one is bit better. Why? I need to consider two things. Thing number one is a transient resistance. Thing number two, what if we have a load current? If we sell, if system one, I don't know who if system one sells energy to system two, we will see it as somewhere in load area. This radius is a max allowable current of load. If there is no reactive power transfer, it will be this point. And the lower load, the higher resistance. Opposite, this area is when system 1 sells to system 2. Something similar should be when system 1 buys from system 2. Import or export. In theory, I can, one of the old theoretical objects is so-called minimal reactance relay. Relay which operates if X reactive resistance is below threshold. Such kind of relay, yeah, it's fine, until you understand what it will trip falsely from load regimes. I need to separate from load regimes, I need a right border. Ideal if consider all possible transient resistance, ideal area looks something like this. Duke. You need to check for works. Duke published in Switzerland. They did a lot of work to find this optimal area. But its problem, it puts too high computing burden on relay. That's why usually something like this is used. Simple line parallel to expected line resistance. So if you have, let's say, 110 kilovolts line, active will be approximately 0.19 ohm per kilometer, and X will be something like 0.49 ohm per kilometer of length. Angle will be somewhere 63, 65, 70 degrees, something like this. So just putting a parallel line creates nice, what I'm doing here, can be created nice operational area. Here is way to define right border as a simple straight line. But sadly, that's not all. I will return to operation area. Before I'll speak to operational area, I need to take a look on coordination. I need selectivity. I need selective operation. It would be stupid if this protection operates on these line faults. I need to separate internal faults from external, and at this moment nothing works better than a simple relative selectivity with a operational time. How it looks, I can put a time scale, and also I can draw in the Rx coordinates. How do we create selectivity zones or operational zones for overcurrent protection? First one, instant, operates instantly, but can protect the whole line because it should be separated by safety margin from the instant zone of the second line. For overcurrent protection, instant zone trips on 1.1 max in external current, 1.1 max external current. Here, what we will see. Why it's 1.1? Because 10% safety margin for the error of current transformers. Yeah? Here I have two values, voltage and current. That means what safety margin should be 10% for current transformer and 10% for voltage transformer. Yeah? 20%. Safety factor should be 1.2? No, 0.8, because it's a minimal resistance relay. So, I need first to set margin for instance zones. Instance zones will, if I take a safety margin for 20%, this will mean what A, B, C, D, what A1 will protect. What will be set point for A1? 80% of, here between A1 and B1, here should be a 20% safety margin to prevent non-selective operation. Meaning what for A1 should be 0.8 of first line reactants. 1. 0.8, 80%. Here is a treat margin for A1. Same thing. B1 should be 0.8. Look this point. It's sorry, it's not B. It's C1 and C1. This point, it's a point BC. At the end of the first line. I will draw it in tensor with different angle. It's a line 2. Let's say line 2 has this way. Okay, line 2 is made of more massive wire, and it's like this is point B. What will be important thing? This coordinate system is for A. For C, this is coordinate system. Where is the zero of resistance for protection A? Here. Where is the zero of resistance for protection C? At the point when first line goes into second, yeah? At the connection point. It's here. Here is the 0 point of resistance for C. Fault, for example, fault number 3. Where it will be for protection A? Here. Yeah? Where it will be for protection C? Backward. At negative resistance. Point for BC. Where is the end of C1? At this point. I should draw it like this. 0.8 L2. 80% of the second line. Here is the end point for C1. Next, C1 should go to C2 and A1 should go for A2. Where A2 should end? I have no other choice, but I need selectivity. Again, it's a question of 20% safety margin. 20%. I need a safety margin. That's me. What f of A2 should be 0.8 xl1 plus 0.8 xl2. 0.6 approximately. This point is approximately 0.6 of the line. 60% of the line. You see this overlap? See what they overlap? One. Here should be 1 delta t times. Here should be time separation. But do you see what this violet is an operation area of the A second zone. Yellow is an operational area of C1, sorry. See they overlap. Redundancy. In case of C1 fold in this part of line, my A2 will cover it, will act as a backup protection. This overlap is a backup operation. Next, I can do A3. In theory, I can make it as sensitive as I can. Just, setting operational resistance something like 80% of minimal possible load resistance. It's in theory, sometimes you can do it, sometimes not. Sometimes you will, usually you will have forward-looking transformer or line and they will set you. The last operational zone should be sensitive. It should be checked against minimal possible load resistance. And next adjustment line, it can go quite far. What it is? Redundance. It's for redundance. It's a backup protection. Good modern distance protection relay. We can have 5 zones forward and 2 more backward. For protection of these buses, yeah, C relay can be equipped also with, it's small, L. Can be equipped with 2 R1 and R2 protective zones for protection of these buses. They act as a backup for bus protection, but very typical, 5 forward and 2 reverse for backup. Now, A3 will be something like this. A3 will overlap C2. And now, bad news. Bad news now. Zone deformation. Bad news. faults here with transient resistance. It's a tree. Small analog tree, maybe large analog tree. But you have fault with transient resistance. At a distance of alpha z. Okay, it's distance alpha. 1 to 1. I need protection scheme. A. C. This is point C. Okay, what's this? A1. And this one is C1. What should I write on red distance? Alpha multiplied by resistance of the second line. See what I'm drawing? Here is ideal RF. Here is theoretical point. My relay should observe. Theoretical. Reality is a bit more complex. I have I1 current and I have current from the second side. Yeah? What will be the result of second current? As a result of second current, we will see something like this. These two I can predict. It's a result of I2 multiplied by RF. Additional resistance. If there is no angle shift between systems, we had no transit, power transit before fault. I can predict it will go straight, but if the higher transit between system before fault, the higher will be virtual negative resistance. Current from the second system introduce kind of virtual reactive resistance to the fault place. It adds it. It should be calculated. It can be well predicted which way it's go, up or down, but in most cases, if you have transit from second system to transit this way, it will go up. If you have transit this way, it will go down. But again, you need to take into account resistance of system. You need to calculate. Anyway, will protection operate here? In only first zone? No. But since it should have, it will be C2. We will see operation of second zone instead of first. as a result of the current from the opposite side. It's a problem of distance protection. Current from the opposite side causes not only move on the active direction, virtual negative will arrive. Where should I take a fold? I can take a fold somewhere here at low kilometers. Here. We can observe quite an unpleasant situation. Transit this way, and this virtual addendum may cause false operation of the A1. You need to sit, take time, take a system model and calculate several folds to understand where most possible shift goes. This kind of shift. Modern railways give you ability first moment. What's this line? For folds at 0, this additive vector to prevent misoperation at near folds 0 kilometers. This border can be shifted. In practice, 5-10 degrees of shift will be enough, but you need to check it. What you need to do? Calculate a near fold at a lower possible current from your side. And you need estimate of transient resistance. Typically take some average numbers, switch from 50 to 100 ohms. In reality, if you're the last one, you don't have a signed paper, directive, we calculate directive transient resistance 100 ohms. If not, take your tower geometry, spend some time with your, usually it's kind of land cadastre service. They do have characteristics of forests. Take characteristics of the trees. Pine trees performs better under voltage than kind of leaf trees. You need to estimate approximate transient resistance, and from that you need to estimate how far this goes. This will give you necessary angle for this border, because your operation characteristic should be a closed figure. You cannot leave this side open. That's a moment number one. Moment number two, it can be done, but should be done very careful. Modern railways allows to tilt upper border. This can be tilted, but it should be, this function should be used with a great precaution, because your next adjustment zone will have here, let's say, 10 degree shift. You need to check this distance. In ideal case, it should be 20%. But for 20%, you will be forced to tilt upper border. You will, to ensure 20%, you will need negative angle. Sums minus 10 degrees. If you both allows you, you can reduce this margin to 10%. But you need to check this point. It's your first zone. It's a lower border of the next protection. It's important. And extreme care should be taken with positive angle. Positive tilt calls non-selective operation. Next moment. Next moment is this line. Why it's not straight? Because in case you have fault and power transit was in opposite direction, vector of power transit will shift. Okay, it's a giant power transit, but it can shift you. So, to ensure robust operation, approximately 10 degrees, 5 to 10 degrees angle should be set. It's for forwarding power transit. So, energy flow from the opposite side causes observable resistance to go up or down. It's a problem. Next, more complex problem. More complex problem is with the power swings. Say a Q feet of the distance protection is a power swing. Assume we have system 1. System 2. This is system 1. One line, two systems. What can happen? Usually, all power system operates synchronously. It's like good symphonic orchestra. But sometimes bad things happen. Example of bad thing: you have a parallel line, and at one bad day, this line disconnects. And what happens? You lost stability. Because transfer capability of this single line is not enough. Okay, two lines, it's 1963 New York blackout. 5 lines from Niagara power. One disconnected, second other overloaded, second disconnected, third, and we have loss of system stability and blackout. When observe loss of stability, it's highly possible, it's 100% possible, what we will see a power swing. There will be actually two different frequencies in parts of system. And we will see moment when a system 1, let's say, it goes up, and a system 2 at this moment looks down. It's a worst case. If you connect them, this is point where voltage is 0. It's called an electrical center of swings. There is a special in Latvian they are AGNA, asynchronous guides novation automatic. Special kind of protection to prevent such modes. Actually, this asynchronous regime protection device will separate systems. And then with the help of frequency reclosing, power balance, energy balance will be re-established, frequency stabilized, and resynchronization may occur, but it's later. At the moment where everything, Houston, it's a problem, we got problem. At the moment when everything gone badly, we will see this asynchronous regime, and in asynchronous regime, at the point center of swings, voltage will be 0. For distance protection, mode of swing will appear as a three-phase fault at the center of swing. And these two protection will operate and will... What will happen? Disaster will go further. We will lose connection. It's a very bad idea. But it's a kind of nature-born problem of distance protection. In case of power swing, distance protection, things what at the center of swings is a three-phase fault. To prevent such operation, all distance protection, real distance protection, are equipped with a special blocking logic, preventing it from operation during power swings. Only super advanced devices existing in not existing. They're theoretically possible, but I didn't see anyone, how to say, in flesh, can operate during the power swings. But no, simple industrial protection, how to say, from the shelf will be locked during the power swing. Older version relied on combination of negative sequence parameters. This scheme is not very reliable. Modern use technique of modern device use technique of called ZZT. It's a first derivative of resistance. The idea that swings are electromechanical processes and they occur relatively slow, while transient faults are fast. For such case, often used something like this. It's a double set of protection areas. here I have active, reactive, double protection zones, vector of line resistance, load, fault goes by some trajectory to the point of that line. There will be two events. One event, two event. When outer and inner zone trips. Time of 2 minus time of 1 gives me an estimation of it's a way to protect ourselves from misoperation during the power swings. Without it, bad things will happen. 100% guarantee. Not even frequency emergency, frequency disaster. No. During connection of power plant. When power plant is synchronized to network, at some moment it goes like and stable. During this, without power swing protection, distance protection will disconnect line. Oh, bye-bye bonuses. Really. Okay, I think it's enough for today. I will continue next time.